Hello everyone, it's September the 4th. Alright, let's go with it. Alright, copy list with a random pointer. I've done this before. A linked list of length n is given such that each node contains an additional... Hold on. Before we start, I do want to mention one thing. A few days ago, I decided to run something on AWS. I chose a free tier a Postgres and a free tier EC2 to run some Docker container and then have them communicate with each other. Everything was fine. I thought it's free tier. I thought they will like reduce my traffic or whatnot. It won't accumulate cost. But I was so wrong. It accumulates cost. Not a lot, but for a few days it accumulates like $2. It's ridiculous. It's supposed to be free. Like, I am sacrificing on the performance. And I was populating a database with not that much data, like 2 gigabytes of data. And it took like, I don't know, 12 hours to populate the whole thing. And I was taking such a big performance hit, so I was expecting the whole thing would be free. Man, it's not. I don't know why. I don't know what happened. Maybe I didn't set it right. But since that, I was like, nah, I'm not doing that anymore. I'll do it, for testing purpose, but other than that, no. No way. I'm not doing that. Anyway, this is just something I want to mention. All right, let's see this one. So linked list, length n. Each node contains an additional random pointer, which could point to any node or null. Construct a deep copy of the list. Deep copy should consist of exactly n brand new nodes. Each new node has its value set to the value of its corresponding. Both the next and random pointer of the new nodes should point to new nodes in a copied list, such that the pointers in the original list and the copied list represent the same list state. None of the pointers in the new list should point to nodes in the original list. For example, if there are 2 nodes in the original list where this, then for the corresponding 2 nodes, x and y, in the copied list. Okay, return the head of the copied. The linked list is represented in the input-output as a list of n nodes. Each node is represented by a pair of... Oh, that's fine. That's just the test cases, right? This and the random. Yoko will only be given a head of the original linked list. As no is point or is pointing to. Okay. So I want to create a copy. So they are already linked. Now all I need to do is make sure that the random one points into the correct thing. The random one needs to point to the correct thing. That's interesting. And the value is not necessarily unique. I mean, we can, right? We can. Like, let's say ON, right? We use external memory. That'll be easy. We just get a mapping out, and then we'll be able to know which one's which. Yes, we get a mapping out. We get a map. How do we get the, let's say Java get, okay, say address of object. Can we do that? No, you can't get the address of object. Oh, wow. Oh. Huh. Then how do I represent it? Hash. Identity hash. Yeah, Basically, that's what I want to do. I want to use a hash to create a mapping between the original and the new one. Right? Original and a new one. So the original, we have a hash as a key, and the new object is going to be the new one, right? And then what? And then we have the mapping, right? The old one, the new one. And then as we go, pointing to, oh, then I need the hash. Yeah, it's object, so I can compute a hash. So okay, that's one way to do, right? You know what? Let's do it first. Now get it done, and then we'll deal with the other ones later. Okay. All right. There's a node, and we need a hash map. What's the identity hash? What is it? Right? T hash. What does it return? A string? I would hope so. My. Oh, we return an int. It returns an int. My bad. That was wrong. It returns an int. So it has to be integer and a node. Right? Mapping. So old to new. Original copy map. Okay. Then we just need to create the thing. Okay, we have original. Okay, we say node ori equals head. All right, and then node dummy equals new node value. It doesn't matter what value. And dummy.next equal to new node head. Oh. It could be null. All right. So we say if head is equal to null, return null. And then this one has .val. And node copy equals dummy.next. Or I can do it this way to make it, I want to make it look nicer. Now origin, copy equal to this, and dummy.next equal to copy. Right. Now we're gonna go through the whole thing. We say while ori is not equal to no, because they both point into the same thing. Okay, they both point into the head. Copy is at head, and the other one is at the head. They're both at the head. Now ori equal to ori.next, and copy.next equals new node ori.val. That's not right. Should do ori.next is not equal to no, right? Then we get ori go to the next, right? We already go to the next, and copy.next equals a new value, then copy equal to copy.next, and then done. Right, now one round is done. Now what we need to do is, we need a hash as well. We need a hash. What do we do? Hash. That's okay. Dummy copy. Dummy original. And then dummy copy.next head dummy original.next equals to new node. No, doesn't really matter. Yep, that should be good. This shall be dummy copy, dummy original, and this is dummy copy. Yep. Okay, so now we can do while this is not equal to no. Right, while original is not equal to no, we'll first handle the ori copy map. Yeah, if current is not equal to null, right, then I shall say copy.next equals new node original.next. Doesn't feel right. Because we have to go in the previous, right? And then we'll go to the next. And that's when I'll go to the next as well. So what we need to do is if original I think it's fine. Equal to, doesn't matter, it's a dummy value. Copy.next equal to this, and then we say if original.next is not equal to val, not equal to no, then we just change it. Copy.next val equals to original.next.val. Right? Otherwise, that doesn't really matter. No, it does matter. It does matter. New node, original.next.val. Right, then we create a new one. But we need to also do the current one, right? We need to do the current one, which means we need to say the original copy map dot put integer systems dot identity hash code hash whom, it shall be the original, right? So the original, and the value shall be the copy, right? We create that, then we do this, then we move both forward, right? We move both forward. Okay, now that we handle everything, we need to go through them one more time, right? We go through them one more time. Basically, at every single point, now we can say node original. We start with head. We say while original is not equal to null, right? Fill out the random pointers. Right, so this is copy the lists. Okay, original is not equal to null. Then everyone we can go for the random pointer. Then we just say, because they all have hash code, so copy shall equal to original copy dot get system dot identity hash original, right? So we get the copy, then we say copy dot random shall equal to original dot random, and it points to something, right? Well, if original dot random is not equal to null, then that shall be original copy map dot get system dot identity hash original dot random. And then original equal to original dot next. Once we're done with all that, now we're gonna return if we have the hash, we probably don't need these two, right? We don't need these two. Yeah, why do you need these two? If I say this is just head, right? This is gonna be, you know, a new node head.val, right? And we're gonna do this copy, and then we say if original next is not equal to null, copy.next equals to this, and then they move forward. Original equal to head, blah blah blah. Then we're gonna return, right? Return original copy map dot get system dot identity hash head. Right? We don't even need okay, let's give this a shot. Copy the list. Oh, I think it should be fine. Yep, it's fine. $138. Create a hash map between the original node and its copy, and go through two passes. All right. Question: do we have a better solution? Well, I had 2 before with Python, so I can take a look. D1 hash map. I use ID. Oh, this is the idea of not using. Hold on, I need to put this one down. I guess I never really think about what if we can do it without using any memory. I think I saw it. It says put a copy node right next to it. Ah, that makes sense, right? You do this, you just insert a node, right? You insert a node, 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 and then go one more time. And then when you go from here to whatever, it's always going to be the one next to it. Oh, that's actually pretty good if you think about it. So this is the O1 extra space method. We put the copy right next to, put each copy node right next to the original one. This way we can easily associate, easily map nodes during the establishment of random pointers. Right, this is still good, and we don't need this. Then we can do this. All we need to do is insert. So insert the copy nodes. Okay, wow, this well, insert one, right? What do we do? I would just say node copy, right? So copy equal to new node original.val. Or I can just say no, I have to do it this way. And then I say node copy node temp equal to original.next, and then temp original.next equal to copy, and copy.next equal to temp. I'd like to put all these 3 in one line. They're all related to each other. Okay. I mean, I don't need this. I need a temp. I don't think I need copy though. I can simply just do temp equal to this, right? And then this will equal to a new node, and then this will be original.next equal to temp. Nah, let's just break it down to 3 lines. Makes more sense. Okay, once these are done, we'll say original equal to original.next. Or I can simply just say original equal to temp. Right? Because temp is the next one. Then we go back up. We hit the whole thing. Done. Then we fill out this original equals head. Original not equal to. And we say if original is not equal to no. Right? If it's not equal to no, then original.next .random equal to original.random.next. Oh, this is so good. This equal to .next. Okay, once we're done, now we need to get it out. Right? Then we say node copy equal to copy head equal to original.next. Okay, and node copy equal to copy head while copy is not equal to null. Right, while copy is not equal to null. Then we need to point, right? So have a copy at the head, and then we need to say next. So we sever this, take the current one out, take the current one out, and then connect it to the next one. Okay. But we are changing the original. How do you preserve the original? We need a pre. Yeah, we need a pre. So copy head, we get it, and then node pre shall equal to head. Right? Okay, so now we're gonna first get it out. We say pre.next equal to copy.next. Let's call it current. Right? So pre.next equal to current.next. So boom, this one is going out. Then current.next shall equal to pre.next. Oh, I can actually do current.next. Right? So current.next equals current.next. So we go up. And we are saying, well, current is not equal to null. I think it has to be current.next is not equal to null. Right? I just change it. Current.next is not equal to null. Then we can do current.next equal to current.next. Right? And go up. Okay, once we do that, then we can move pre equal to pre.next, current equal to current.next. So this will be able to separate the two. Now once we separate the two, we shall return copy head. Should be head. Okay. All right, let's see. Is this one working? Some part is wrong. That's all right. That is absolutely all right. Okay, let's go think again. Is this right? Node is the head. Now a temp. Okay, original is not equal to null. Temp is this one, the next. Okay, that's temp. And the original next equal to a new node, which has the same value as original. Okay, and this new node, the next, right, equal to the temp, and origin equal to temp. I think this is correct. Let's kind of go to the last one. temp will be null. And original next will be this. So next dot next equals temp. Okay, so I think this one's correct. This one might be wrong. Split out the copy nodes. Okay, original will go back to head. Okay, well, original is not equal to null. Original, the random. If original random is equal to, oh, wait, no, hold on, this is right. If original random is not equal to null, if original the random is not equal, if it's equal to null, then it should be null, right? Oh, holy crap. The random, this one can point to itself. But that should be fine. That should be fine. If it's null, then they basically mean it's next, the random, we don't change. Right? Okay, so original random is not, so it's pointing to something. Then I say it's next. This is called copy nodes. So copy node of random shall equal to original random, okay, dot next. I think this one is correct. Once we're done, origin move forward. We have to move dot next, have to move two things. I think this is right. So probably problem is here. Okay, problem probably is here. Copy head is head dot next. Should be right. Copy head is head on next, and a current is at a copy head. Pre is at a head. That's correct. And we say current dot next is not equal to null. Okay. Then what do? We say pre dot next equals current dot next. Okay. So, okay, that's good. And a current dot next shall equal to current dot next dot next. So this one connect here. And then pre equals pre dot next. Current equals current dot next. Is that not right? Let's see. We have original copy, original copy, original copy, no. Right? So this is the current. This is pre. Pre dot next equals to current dot next. So this one pointing here. Current dot next equals current dot next dot next. So this one pointing here. Right? Is perfect. And then pre, so pre become here. Current become here. Okay, so let's simplify it and let's point into null directly, see what happens. So this is null, right? Then we say current dot next is not equal to null. Ooh, this one still connects. Oof. What should happen is, so it gets out, right? So when it gets out, pre is here, current is here. So we should do pre dot next. So once we get out, I should do pre dot next equals to null. Okay, let's see. Change this one line. Does it work? All right, pre dot next equal to null. Doesn't work. Yep, that's the one. That's the missing part. was good. It was good. I think I did it better than last time. Now use a dummy. Yeah, that's fine. Okay, okie dokie. That was good. And we will move on to our daily dose of JavaScript. Okay, so we're done with this. Array reduce transformation. Hold on, I have to run. I'm running some code. I'm running something else. I need to. cd open cv services. Okay. Hold on, let me take a look. All right, everything's working. Salary. One more thing to check. 9,000, right? Yep, I think everything is working. That's good. Okay. All right, let's get back to this. Given an integer array nums, a reducer function, and an initial value, return a reduced array. A reduced array is created by applying the following operation: val equal to function initial, then this val function val function until every element in it has been processed. The final value is returned. The length should return this without using built-in reduce function. Okay, so it can be an array, right? We can do array. Nums is function, nums, a function, an initial value is a sum. So the function will call the accumulated. Yeah, I think this one is probably not that hard. So function initiates, we have initial, so we can say let res equal to init, right? And then for let n of nums right? Then we say res shall equal to function res n return how's that? How's that look? This one, right? Looks all right. Yep, looks all right. I bet somebody will want to use the recursion for this. I don't think it's necessary. 5 different methods. Oh, reduce right. Remember that? reduce right, reduce left. I was in the, what was that? Scala. Debounce, given a function and a time in millisecond. Return a debounced version of that function. Debounced version is a function whose execution is delayed by t milliseconds and whose execution is cancelled if it is called again. Within that window of time, the debounced function should also receive the passed parameter. For example, let's say t equals 50 and the function was called at 30, 60, and 100. The first two function calls will be cancelled and a third function call will be executed at 150. Input event. T equals 50. The function was called at 30. So it called the first, right, with 50 milliseconds. So it shall not be called again until 50. Huh? But at 60 milliseconds, the first two call be cancelled. Why? Execution is delayed t milliseconds, and whose execution is cancelled if it is called again within. So within the 50 millisecond, right? Within the 50 millisecond, if you call it again, it will be cancelled. The first two function calls will be cancelled. Why is this one gets cancelled? Each rectangle represents 1 millisecond, and the debounce time is 400 milliseconds. Each color represents a different set of inputs. All right, let's try to understand this. Input at this. What's the green? What's the blue? I don't understand. It's delayed by, so it's delayed by 50 milliseconds. And the function was called, oh, it did not call at the beginning. It's just say, or delay by 50. So we're going to call, so this is a timestamp when we call it. So at 30 milliseconds, we call it. So delay 50, it will be called at 80. Makes sense. It will be called at 80 milliseconds. So the 60 will be cancelled, and then the 80, it gets first execution, right? And then it called a 100. It called a 100, and it will be second. It will be executed at 150. Okay, that makes sense. If it called at 35, the first. If t equals 35, the first call will be cancelled. If instead t equals to 35 milliseconds, it's called at 30, 60. Wait, hold on. I still don't. This function was called at 30. And whose execution is cancelled if it is called again within. Oh, it's get cancelled. So we call it 30, which says I'll delay it until 50. And then, so that means at 80, we shall do the function call. We shall execute it. But then we call it 60, which cancels the previous one. So at the current, there is no function to be executed, right? At the current, there's no function to be executed. And then we call it 100 and the third. Now that makes sense. This one's the same, 35, right? And then because if t equals to 35 and we have first call at 30, so it shall be executed at a 65 and the second call 60. Nah? No, I think it is. It is. We are call. The first two calls. Let me read it again. A debounce function is a function whose execution is delayed by t-max and whose execution is cancelled if it's called. Oh, I think it just canceled the previous one, but the current one is still going on. So we call it at 30, okay? So it shall execute at 80, but we call it 60, so the previous one got cancelled. Now we are looking at 60, and this one should be executed at 110, but then I call it 100, and then this one got cancelled, so this is the only executable one. In this case, we start at 30, so we shall execute at 65, but we call it 60, so this one gets cancelled. So at 60, we shall execute. Now that makes sense. Now that makes sense. Okay, so we figured out how this one's going. How are we going to implement it? How are we going to implement it? Debounce. I mean, the stupidest way is to take the, we can take the timestamp. We can always take the timestamp. Let's do the stupid way first to take the timestamp, right? Which means each time we call, we will return a function, right? We return a function. So each time we call this function, right? Each time we call this function, we will check if the current time and the previous time, right? So what I need is a timestamp of the previous. So it's kind of the lazy solution, right? So let previous time. I'll just do a previous time. We have to. Wait, hold on. So if it's smaller then, right? So previous time we can equal to minus 1. Minus 1. When we start the first call with the previous time. So the previous time should be as small as possible. Do we have, right, do we have a negative infinity? That's a good question. JavaScript. Negative infinity. Do we have this? We do. Number dot negative infinity. All right, so that's the previous time. Okay. Now, each time we call this function, we say current time equals new date. Right, and if current time oh, but hold a second. You need to execute. You do this, you don't execute. Have to say set timeout. Right? Have to set timeout. So maybe we need to do both. Right? We do both. So if current time minus pre-time, right? Minus pre-time. If current time minus pre-time is larger. I think it's larger. It cannot be equal. If it's larger than t, right? Which means the amount of time this is current execution and the previous execution. When this gets called, I know the previous execution, previous time. So if it's larger than the t, right? Larger than the t. Wait, hold a second. No matter what, you will do the timeout, right? Every time you have to redo the timeout. It's just, yeah, every time you have to do the timeout. Every time you do. All what you need to do is to cancel the previous timeout. Wait, how do you do cancel timeout? Hold on. Cancel timeout. Clear timeout. The global clear timeout cancels the timeout previously established if the parameter provided does not identify a previous slash. This method does nothing. Was returned by the previous timeout. So I think that's like a debounce already. So let's not read it. I think, yeah, it's so I need to say let timeout ID, right? So no matter what, when we call a function, when we call it, there should only be one timeout ID. I think that's the thing. There should be only one timeout ID. So when we call the function, we need to know if but doesn't make, hold on. So when we call, right, we call at a certain time and we say set timeout and it will execute, right? And then we call it again. Then we cancel the previous one. And then we set up a new one. And we call it again. Then it will be executed. Yeah. I don't really think. I think, isn't this just this? Every time we call it, regardless, I will clear timeout ID, right? And then set timeout, timeout ID, set timeout, function calling the arguments and a t. I think this is sufficient. I think this is sufficient. Well, I'm not sure, but we're gonna give it a shot. Is this sufficient? Yeah, it's sufficient. We just clear out the previous one and that's it. Because if the previous one has been executed, that's fine. You just clear it out. It doesn't really matter. If the previous one has not been executed, you just clear it out and then you set up a new one. Yeah, it looks tough, but I think this should be fine. Yeah, this is fine. Good. Good. Yeah, this no special trick needed. Each time the function is called, simply clear out the previous timeout. If the previous timeout has been executed, has been completed, no harm done. Otherwise, we cancel it and set up a new one, a new timeout. That's it. That's basically how it's gonna be. Yeah, I'm pretty confident. I think this is the right. Limits the rate at which a function gets called. It works by delaying the execution of a function until a certain amount of time has passed without any additional function calls. Yep. This is good, but I don't think this is a good example. If I were the user, I like to see the things getting updated immediately. But I guess there will be cases where debounce is very useful. Okay. Ooh. Oh no, this is the regular problem. I think we did we do all the JavaScript here? Not all of them. We just hit the first bunch. Should be good enough. That'll be enough for us to go through. Alright. That shall be it. Minimum reverse operation. Oh, that's the problem. I remember. I don't think I can solve this. I forgot. Alright, anyway. That'll be it. That'll be it for today. I will see you guys again tomorrow. Adios.